Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com.
Hello.
Today, we're going deep into Unit 1 of your physics syllabus, electric charges and fields. Our mission is simple: to understand the electric field so clearly that it becomes completely logical and, of course, exam safe for you.
It's a topic that can feel a bit abstract.
It can. So let us start with a very simple question. You've probably done this yourself. You rub a balloon on your hair, it gets charged, and then it sticks to a wall.
Yes.
My question is, how? How does the balloon exert a force on the wall when there is only empty space between them? How does one object know the other is there?
That's a good question. I mean, you assume maybe the air is doing something.
Yeah.
But what if it were in a vacuum? Feels like it. Well, like magic.
Exactly. It's what physicists used to call spooky action at a distance. And for a long time, there was no good explanation for the mechanism. We need some kind of invisible intermediary. And this concept, the electric field, is the answer. It's not just theory, it's used everywhere. For example, in big power plant chimneys, they use something called electrostatic precipitators.
What do they do?
They create a very strong electric field inside the chimney. This invisible field literally grabs tiny pollutant particles out of the smoke, cleaning the air before it goes out. Real, tangible work.
So this invisible field is actually doing something physical.
It is. Now, here's a hook that's critical for your exams. It's about how this influence changes with distance. It follows an inverse square relationship.
Right, like in gravity.
Precisely. So if you double the distance from a charge, the field strength doesn't just become half. It drops to 1/4 of its original value. It gets weak very, very quickly.
Okay, 1/4. That's a steep drop.
Understanding that is key. Now let us unpack the core idea. The electric field, which we denote by E, is the solution to this action at a distance problem. We change the story. We no longer say charge A pushes charge B directly. Instead, we say charge A first creates a condition, a distortion in the space all around it. That is the electric field.
So the charge modifies the space.
Yes. Then it is this field which exerts the force on charge B. It's a two-step process. Charge creates field, and field exerts force.
I understand the process, but is the field a real thing? Or is it just a mathematical tool, a trick to make the calculations work?
That is a brilliant question, and the answer is why the field concept is so powerful. If the force was instantaneous, it would mean that if charge A moved, charge B, no matter how far away, would feel it instantly.
Which can't happen.
Right. Nothing can travel faster than the speed of light. The field concept fixes this. If charge A moves, it first has to disturb the field right next to it. That disturbance then travels or propagates outward at the speed of light.
Ah, so there's a time delay.
Exactly, a time delay. And because this disturbance carries energy and momentum, we are forced to conclude the field is a real physical entity. It's not just a calculation trick.
That makes much more sense. It makes the whole process physical, not magical.
Yes. Now, for a good analogy, imagine the electric field is like an invisible weather map in space.
A weather map.
Yes. This map shows the, let's call it, electrostatic pressure at every point. A region with a strong field is like a high-pressure zone. Any charge you place there will feel a very strong push.
And this map has directions, too.
It must. It's a vector map. So at every point, there's a little arrow that tells you the direction a positive charge would be pushed. It tells you both the strength and the direction of the potential force.
Okay, that visual helps.
Let's build a mental image from that. Think of a single positive charge as a tiny sun. This sun is radiating an invisible pattern of intensity into space.
Right.
Very close to the sun, the space is, say, bright red. That means a strong field. As you move away, it fades to pink, then becomes very pale. The field gets weaker.
And the direction.
Since our sun is positive, it repels other positive charges. So the field arrows, the vectors, must always point radially outwards, away from the positive source.
And if the source was negative?
The arrows would all point radially inwards toward the negative source because it would pull a positive charge in.
Okay, that's clear.
Yeah.
But to measure this field, to draw this map, don't I have to place a test charge there to feel the force? How can it exist if nothing is feeling it?
That is the operational point. We use a test charge, let's call it Q-test, only as a measuring device. Like a thermometer measures temperature. The temperature exists even if the thermometer isn't there.
I see.
The field E is a characteristic of the source charge system alone. The test charge is just a probe we use to reveal that pre-existing property of space.
Got it. The field is there regardless.
Gotcha. So let's build the formal definition now, step by step.
Okay.
To define the field at a point, we place a very small positive test charge, Q test, at that point.
Yeah.
Then we measure the force F on it. And finally, to make it independent of our measuring device, we simply divide the force F by the magnitude of the test charge. This gives us the definition. E is equal to F divided by Q test. Now let us see how NSUIT formally defines this concept.
The NSER definition is the electric field at a point, the force per unit charge exerted on a positive test charge placed at that point. E equals F test.
Thank you. That formula is your anchor. From it, we get the SI unit. Forces in newtons, charges in coulombs, so the unit is Newton per coulomb, NC.
NC, right.
And because force F is a vector, the electric field E must also be a vector. Its direction is the same as the force on a positive charge.
Okay.
And we must also know the formula for the field from a single point charge Q. That is E equals K times the absolute value of Q divided by R squared.
E equals KQRO1. It only depends on the source and the distance.
Exactly. And the most useful relationship to remember is F equals QE. This tells you the force on any charge Q you place in a known field E.
F equals QE.
But be careful. If the charge Q is negative, the force F will be in the direction opposite to the field E.
Right, because of the negative sign.
Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com.
Okay.
Now, let's do a very simple example just to get a feel for the numbers. Let's say we have a source charge Q of plus 2 times 10 to the power minus 6 coulombs. So 2 microcoulombs.
A small charge.
Yes. And we want to find the field E at a distance of 0.3 meters, which is 30 centimeters.
Okay.
We just use the formula E equals KQRI array. When you put in the values, you get a surprisingly large number. The field E is 2 times 10 to the power 5 newtons per coulomb.
200,000 newtons per coulomb. That seems huge for such a small charge.
It does. It tells you just how strong the electrostatic force really is. It means that if you could place 1 whole coulomb of charge there, it would feel a force of 200,000 newtons.
Wow.
Of course, we never deal with a full coulomb, but it shows the power of the field. And since our source charge was positive, the direction is radially outward.
Outward.
And to connect this to the rest of the unit, the electric field is the perfect tool for the superposition principle.
Also,
Instead of calculating the force on a test charge from 10 different source charges one by one, you first calculate the net electric field, E net, created by all 10 of those charges at that point.
so you find the property of the space first.
Exactly. Then finding the force on any test charge is just one simple multiplication. F equals Q test times E net. It's much more efficient.
That makes sense.
Good. Now let us shift to something very important for exams, the silent killers. These are the common misconceptions that cause students to lose marks unnecessarily.
Okay, what's the first one?
The biggest one is confusing field and force. Students will write, the electric field is the force. They use E and F as if they are the same thing.
So how should we correct that thought instantly?
The correction is, the field is the force per unit charge. Remember, E equal FQ. The field is the cause, the condition in space. The force is the effect that a charge feels because of that field.
So the field is the potential for the force, not the force itself.
Perfect way to put it. The field exists even if no charge is there to feel a force.
Okay. What's the second misconception?
It's about field strength. Students often think the field is stronger where there are more charges.
That seems logical on the surface. More charges, more influence.
It seems logical, but it's wrong. You must remember the one by R-squared dependence. The field depends on the source charge Q and the distance squared. A single, very strong charge far away can create a much bigger field than 10 weak charges that are very close by.
So it's not about the number of charges, but their strength and distance.
Precisely. Always focus on the source charge and its distance.
And the third one?
This one is a direction mistake. Students say the field points toward negative charges, which is true, but they forget the reason why. The convention is key.
What is the reason?
The electric field direction, by definition, is the direction a positive test charge would move. A positive charge is attracted to a negative source, so it moves toward it. That's why the field vector points inward.
So you always have to think from the perspective of a positive test charge.
Always. Field points outward from positive and inward toward negative. Remembering the why will save you marks.
Got it.
Now, to make sure all this stays in your memory, let's use some anchors.
Okay.
For the main formula, E equals F divided by Q, just use the mnemonic EFQ. Electric field equals force per quantity of charge. EFQ.
EFQ. Simple.
And a phrase to remember the concept. The field is the force per unit charge. It's space's way of saying how hard it will push a charge.
It's a good way to think about it.
And finally, a physical gesture. When you are revising, use your hand. For a positive charge, push your hand outwards from your body, showing the field radiating out.
Okay.
For a negative charge, pull your hand in towards your body as if you're pulling something in. This will help you remember the vector directions.
Out for positive, in for negative. I'll try that.
Excellent. Now, to summarize our entire deep dive in 3 key points for your exams. Summary, point 1. The electric field, E, is defined as the force experienced per unit positive test charge. The formula is E equals F divided by Q.
Right.
Summary, point 2. The field is a vector. Its magnitude depends on the source charge Q and decreases with the square of the distance, R. The direction is radially outward from a positive charge and inward toward a negative charge.
Understood.
And summary, point 3. The field is a property of the source charges and the space around them. It exists independently of any test charge. This concept is the mechanism that explains electric force across a distance.
Very clear.
To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam, right, Brian?
Yes, PROFSAM.com. We wish you the very best for your studies, students. We will meet again soon for another deep dive.